February 1944, somewhere inside a German weapons laboratory. Buried beneath layers of concrete and secrecy, an engineer stood motionless as another test round was fired. He had seen this moment too many times before. The shell screamed out of the barrel. For a split second, hope flickered, then it failed. The electronics inside the shell disintegrated instantly. Glass shattered. Filaments snapped. What remained clattered onto the test range as useless fragments. When the echoes faded, the silence that followed felt heavier than the explosion itself. This was the 50th failure, not a minor flaw. Not something that could be fixed with a small adjustment. It was total collapse, the same ending every time. Months of calculations. Years of research. Some of the best engineers in Europe. All defeated in less than a millisecond by the brutal physics of the gun barrel. The engineer didn't need to look at the wreckage to know what had happened. He already understood the problem too well. The acceleration, the spin, the heat. Forces so violent that no electronic device should survive them. Every test confirmed the same conclusion: this weapon could not exist. And yet, intelligence reports told a different story. Across the Atlantic, American artillery shells were doing something impossible. They weren't exploding on impact. They weren't detonating based on carefully calculated timers. They were bursting in midair at exactly the right moment, as if the shell itself knew. When it was close to its target, aircraft were being destroyed with frightening efficiency. Barrages were suddenly precise. Defensive fire that had once relied on luck now felt deliberate. The Germans had a name for it. A proximity fuse. The idea was simple. Engineering was supposed to be impossible, and standing there, surrounded by the remains of another shattered prototype, the engineer faced a terrifying realization. Germany wasn't losing because it lacked ideas. It was losing because the Americans had solved a problem that physics itself seemed to forbid, and no one in the right could figure out how they had done it. Since the first cannon was fired, artillerymen had dreamed of the same impossible thing, a shell that knew when to explode. For centuries, gunners were forced to choose between two deeply flawed options. The first was the impact fuse. Simple, reliable, and almost completely useless unless the shell struck its target directly. Against fortifications or massed troops, it could work. Against a fast-moving aircraft, it was nearly worthless. Hitting a plane with a solid metal projectile was like trying to strike a bird in flight with a thrown stone. The second option was the timed fuse. This was an exercise in mathematics and guesswork. Gunners had to calculate how long the shell would remain in the air, factoring in muzzle velocity, distance, wind, air density, and target movement. A fuse was then set to detonate after that precise interval. In theory, the shell would explode near the target. In reality, even the smallest error meant the burst came too early or too late. Against aircraft, the failure rate was staggering. Anti-aircraft batteries could fire thousands of rounds and achieve nothing more than noise and smoke. Estimates varied, but bringing down a single enemy plane often required several thousand shells, sometimes more than 10,000. The sky would be filled with explosions, yet the aircraft flew on unharmed. Every major military power understood the problem. Air power was becoming dominant, and artillery had no reliable way to stop it. What gunners needed wasn't better aim or faster guns. They needed intelligence inside the shell itself. A shell that could sense when it was close to its target. A shell that didn't rely on luck or perfect timing. A shell that exploded at the exact moment it mattered. If such a weapon could be built, it wouldn't just improve artillery. It would change the balance of warfare entirely. The problem wasn't theory. It was physics. On paper, the idea of a proximity fuse made perfect sense. Detect the target. Trigger the explosion. Simple. But the moment engineers tried to move from diagrams to reality, they collided with forces that no laboratory experiment could truly prepare them for. When an artillery shell leaves a gun barrel, it is subjected to violence unlike almost anything else engineered by human hands. In the fraction of a second it takes to accelerate down the barrel, the shell experiences more than 20,000 times the force of gravity. That shock alone is enough to pulverize most mechanical systems. At the same time, The shell is spinning over 25,000 revolutions per minute to stabilize its flight. That rotation creates enormous centrifugal forces, trying to rip every internal component outward, tearing circuits apart from the inside. Wires stretch, connections snap. Anything fragile simply disintegrates, then there is the heat. For a brief moment, temperatures inside the barrel rise to levels hotter than molten steel. It doesn't last long, but it doesn't need to. Delicate electronics don't fail gradually under those conditions. They fail instantly. A proximity fuse required electronics. Specifically, vacuum tubes, thin glass envelopes, fragile filaments, components that could be destroyed by a drop from a table. Asking them to survive gun launch forces was like asking a light bulb to endure an earthquake. Every German engineer who studied the problem arrived at the same conclusion. No matter how elegant the design, no vacuum tube could survive that environment. The physics made the idea self-contradictory. So, Germany abandoned the tube, and instead of trying to defeat the gun barrel, they began searching for ways to avoid it altogether. Between 1933 and 1945, Germany launched more than 50 separate programs to build a working proximity fuse. These weren't minor side projects. They were serious, well-funded efforts spread across military branches, private firms, and top universities. Each team attacked the problem from a different angle, convinced that if one approach failed, another might succeed. Some designs relied on acoustic sensors, attempting to listen for the sound of an approaching aircraft engine. Others experimented with electrostatic triggers, hoping to detect disturbances in an airplane's electrical field. There were infrared detectors meant to sense engine heat and radio-based systems that functioned like miniature radar sets. Each concept worked briefly in the laboratory. None survived being fired from a gun. Every test followed the same pattern. The shell was loaded. The gun fired. And in the violent instant of launch, the delicate internals were destroyed. Circuits fractured. Components shifted. Sensors that had functioned perfectly seconds earlier were reduced to scrap. The detection method didn't matter. The moment the shell met the gun barrel, the physics took control. The fragmentation of Germany's research effort made the problem worse. The Luftwaffe and the Army competed instead of cooperating, duplicating work while withholding breakthroughs. Resources were divided, priorities shifted, and promising designs were abandoned when funding disappeared or authority changed hands. By 1944, the pattern was impossible to ignore. Dozens of projects. Years of effort. Nothing operational. The German High Command reached a grim conclusion. A gun-fired proximity fuse was theoretically unsound. The idea violated the limits of materials and electronics as they understood them. The program was officially deprioritized, and attention shifted to missile-based fuses where acceleration forces were lower. It was a rational decision, based on everything German engineers knew. What they didn't know was that, across the Atlantic, the Americans had already found a way to make the impossible routine, and were quietly preparing to unleash it on the battlefield. In August 1940, the United States wasn't even at war. Europe was already burning, but across the Atlantic, America was still officially neutral. Yet the U.S. Navy was watching events closely, and it was afraid. If modern air power could devastate fleets at sea, traditional anti-aircraft fire would no longer be enough. That fear led to an absurd assignment. A physicist named Merle Tuve was told to do what others had already declared impossible. Build a proximity fuse that could be fired from naval guns and survive. Not theorize it, not study it. Build it. Tuve understood the challenge immediately. The heart of the problem wasn't detection, it was survival. Any working fuse would need vacuum tubes, fragile glass devices that acted as the brain of a tiny radar system. If the tubes failed, everything failed. The breakthrough didn't come from a military laboratory or a revolutionary new theory. It came from an unexpected place: hearing aids. For years, American consumer electronics companies had been shrinking vacuum tubes for everyday use. Hearing aids needed components that were small, cheap, and durable enough to survive daily movement, drops, and vibration. By accident, industry had already solved part of the military's problem. Instead of trying to defeat the forces inside the gun barrel, American engineers worked around them. They embedded the miniature tubes in blocks of flexible resin, allowing the components to flex slightly under stress instead of shattering. The solution wasn't elegant. It was practical. Then came the testing. They fired shells from makeshift cannons built from gas pipes. They dropped components from rooftops. They shot them with small caliber bullets. If a part failed, it was redesigned and tested again. No theory survived contact with reality. By early 1941, vacuum tubes were routinely surviving forces exceeding 20,000 times the pull of gravity, what German engineers had declared impossible. American engineers had turned into a manufacturing problem and solved. The impossible wasn't just possible anymore. It was repeatable. By 1942, the proximity fuse worked, and it worked too well. Tests showed that artillery shells no longer relied on luck or perfect calculations. They detonated automatically at the most lethal moment, scattering fragments exactly where enemy aircraft or troops were most vulnerable. Against drones and test targets, the results were undeniable. A handful of shells could do what thousands once failed to achieve. That success created a new problem. American military leadership immediately understood the danger. If even a single unexploded shell fell into German hands, the consequences could be catastrophic. The technology inside the fuse wasn't magic. Given time, German engineers could study it, copy it, and turn it against Allied bombers and ground forces. A German proximity-fused air defense network could devastate entire formations. So, the weapon was locked away. The proximity fuse was classified at the highest level, placed in the same secrecy category as the atomic bomb. Strict rules governed its use. It could only be fired over open water, where any dud would sink beyond recovery. Naval vessels in the Pacific were authorized to use it against Japanese aircraft, but ground forces in Europe were forbidden for soldiers fighting across North Africa, Italy, and France. The fuse might as well not exist. By 1943 and into most of 1944, millions of proximity fuses sat sealed in crates inside guarded warehouses. They were ready, they worked, and they were not allowed to be used. Infantry fought with traditional artillery while a revolutionary weapon waited only miles away. This created a cruel paradox. A device capable of saving countless lives was withheld because it was too effective. Every day it remained unused, casualty lists grew longer. Then, in December 1944, the situation changed. German forces launched a massive surprise offensive through the Ardennes. American lines buckled. Entire units were cut off. The war in Europe reached a moment of crisis. And suddenly, keeping the secret mattered less than surviving. When German forces surged through the Ardennes in December 1944, everything changed overnight. The attack shattered Allied expectations. Units that believed the front was quiet were suddenly overrun. Roads clogged with retreating troops. Entire divisions were cut off in forests and frozen valleys as German armor pushed forward through fog and snow. For Supreme Commander Dwight Eisenhower, the situation was desperate. He had known about the proximity fuse for months. He had watched it sit unused in warehouses while his men fought with weapons that were no longer good enough. Now, with his armies on the brink of collapse, secrecy became a luxury he could no longer afford. Eisenhower demanded the weapon's release. Within days, artillery units across the Ardennes received unfamiliar crates marked with new instructions. Gunners were given hurried training. Many had never fired a proximity fuse shell before. There was no time for extended testing. The shells were loaded, the guns elevated, and the first barrages were fired into the winter fog. The effect was immediate and horrifying. These shells didn't bury themselves in the frozen ground before exploding. They detonated in midair, 30 to 50 feet above German positions. Shrapnel rained straight down, bypassing trenches and foxholes that had protected soldiers for generations. Wooden bunkers were shredded. Log reinforcements offered no shelter. Units caught in the open simply froze, unable to move under the invisible bursts above them. Men who had endured months of artillery fire suddenly found themselves defenseless. Some German soldiers broke and ran not away from the explosions, but toward American lines, surrendering in panic just to escape the air bursts. The proximity fuse did more than kill. It destroyed confidence. It turned cover into a lie and safety into an illusion. Under those detonations, formations stopped advancing, orders went unheeded, and the momentum of the German offensive collapsed. In the Ardennes, artillery didn't just stop an attack. It broke the enemy's will to fight. After the war ended, Allied investigators combed through captured documents, laboratories, and half-finished prototypes, searching for an explanation. How could Germany, home to some of the world's most advanced scientists and precision engineers, fail to build a weapon the Americans had produced by the millions? The answer was not intelligence. It was not my imagination. And it was not scientific understanding. Germany understood physics. Their engineers had identified the same challenges, proposed many of the same solutions, and reached many of the same intermediate breakthroughs. In isolation, some German designs even worked, briefly, in carefully controlled conditions. What Germany lacked was something far less glamorous, but far more decisive: a consumer electronics industry capable of turning fragile laboratory devices into rugged, disposable products. American industry had spent decades solving problems that German military engineers never needed to confront. How do you make electronics cheap enough for mass markets? How do you make them small enough to fit in a pocket? How do you make them durable enough to survive everyday abuse? Hearing aids, radios, and consumer gadgets demanded answers to those questions long before the military ever asked. By the time war came, American factories already knew how to produce millions of identical electronic components with consistent quality. When the proximity fuse moved from the laboratory to production, the United States didn't need to invent a manufacturing system. It already had one. Germany didn't stay. Its electronics industry was fragmented, specialized, and optimized for precision, not volume. Research programs were divided among competing branches of the military, each guarding resources and breakthroughs. Even when solutions appeared, they couldn't be produced fast enough or reliably enough to matter. Factories that once made hearing aids, radios, and household electronics in America now produced weapons that transformed the battlefield. The proximity fuse was not just an invention. It was the product of an industrial ecosystem. Germany never stood a chance, not because the idea was beyond them, but because the ability to manufacture it at scale simply didn't exist. Wars aren't always won by better ideas. They're won by the ability to build those ideas at scale, under pressure, and faster than anyone else. If you want more stories about the hidden technologies that quietly changed history, subscribe to the channel and stay with us, because the most powerful weapons aren't always the loudest ones. Sometimes they're the ones nobody believes are possible.